Welcome to this explainer. I am absolutely thrilled you're here today because we are looking at one of the most exciting, frankly mind-blowing leaps happening right now in the field of artificial intelligence. Look, for the last few years, we've all been completely spoiled by large language models, right? We use them every single day to write code, draft emails, figure out complex problems. But those models rely purely on text. Well, today, we are taking a massive leap forward. We're talking about moving away from AI that only understands text symbols and diving into native multimodal intelligence. We're talking about AI that can actually see, hear, and interact with the messy, complex physical world around us. And this whole shift forces us to ask a really profound question. Is language alone enough to achieve true, real-world AI? I mean, think about it for a second. Next token prediction, basically just guessing the next word in a sequence over and over, that has given us models with incredible reasoning capabilities. But the physical world, and honestly even the digital world we surf every day, it's fundamentally multimodal. It's not a neatly organized textbook. It's a chaotic blend of sights, sounds, and movements. So if we want AI to truly understand our reality, language is just not going to cut it on its own. Okay, let's dive right into this roadmap. First up, beyond text only. Second, tokenizing the physical world. Third, the rise of omni-models. Fourth, optimizing the AI brain. And finally, fifth, the next AI frontier. Let's get into it. Section 1. Beyond text only, the multimodal imperative. So the current text-only paradigm, as amazing as it is, essentially hits a brick wall when it comes to physical world applications. If we're going to build AI systems that interact with us in real time, out in the real world, they can't just be reading transcripts. They need to process live images, stream video, analyze audio on the fly. True intelligence isn't just about reading a Wikipedia page. It's about taking that symbolic, book-smart knowledge and seamlessly marrying it with raw sensory input from a camera or a microphone. The AI has to process the world exactly as fluently as it processes a written sentence. Section 2. Tokenizing the physical world. The universal language of AI. To understand how we actually do this, we need to talk about tokenization. Tokenization is essentially the AI's universal translator. See, a transformer architecture, which is the underlying engine of modern AI, it loves sequences. It absolutely thrives on processing things one after another. But an image isn't a sequence, right? It's just a big, flat block of pixels. Audio is a continuous, messy waveform. So tokenization is this vital engineering trick of taking those wild, diverse signals and converting them into standardized sequential units, tokens. Once everything is a token, the AI can process a picture using the exact same mathematical machinery it uses to read a paragraph. So how does that actually happen for a picture? Well, it's something called the patchify process. Imagine taking a photograph and just drawing a grid right over it. You divide it into standard little squares, say 16 by 16 pixels. That's step 1. Then in step 2, you run a continuous encoder on those tiny patches to turn the pixel colors into a string of numbers. That's your vector representation. Finally, step 3, you just line those numbers up in a sequence. Boom! You've just successfully turned a two-dimensional photograph into a simple, logical sequence of image tokens that a transformer can easily digest. It's like turning a picture into a very specific sentence. And once you grasp that, video actually becomes incredibly straightforward. Video is simply processed as a sequential concatenation of patchified image frames, basically a super fast flipbook of tokens. Audio follows a really similar logical transformation from a waveform into tokens too. So suddenly, moving pictures and spoken words are all just treated as a rapid sequence of these uniform data patches. The messy physical world has literally been translated into the mathematical language of the machine. Section 3. The rise of omni-models. From passive understanding to native generation. Now there is a massive paradigm shift happening right now. Early multimodal systems, they only handled multimodal input, meaning you could show the AI picture, sure, but it could only talk back to you by typing out text, which, that's great if you wanted to answer a question about a photo, but it's pretty limited. Omni-models, on the other hand, represent a total game changer. They take multimodal input and natively generate multimodal output. You speak to it, it speaks back out loud. You show it a picture, it draws you a brand new picture in response. The whole shebang. It operates completely fluidly across all inputs and outputs within one single system. But figuring out the best way to actually build these omni-models, well, it sparked a fascinating engineering showdown. Let's look at two totally different approaches. On one side, we have the chameleon model. Its hypothesis was super simple. Just force everything to be a discrete token, exactly like text. The trade-off? Doing that leads to significant information loss for images. It just gets kind of blurry and loses detail. Now, on the other side, we have the transfusion model. This one is a bit more complex. It uses standard text prediction for words, but it blends that natively with a diffusion process for images, basically meaning it learns to gradually form images out of static noise. Transfusion ends up giving way better image generation quality, and it's highly token efficient. And this brings us to a massive dilemma currently gripping the whole field of AI research. See, mathematical representations that are incredibly efficient for generating or drawing a beautiful image, things like variational autoencoders or VAEs, they're actually quite poor when you ask the model to understand what is inside an image. Conversely, continuous encodings are fantastic for image understanding, but terrible for generation. Right now, the field is seriously struggling to unify both generation and understanding into one single, elegant mathematical encoding. Simply put, what draws well doesn't understand well and vice versa.
Section 4. Optimizing the AI brain, wiring the mixture of transformers.
So, because engineers can't just sit around waiting for the perfect unified encoding to be discovered, they are literally rewiring the neural networks themselves to solve the problem. Enter the mixture of transformers, or MOT. Think of this like giving the AI a highly specialized brain. Instead of forcing text, audio, and images to cram through the exact same mathematical pathways, MOT gives each modality its own independent set of parameters. It gets its own specialized language center and its own visual center. But, and this is absolutely crucial, they maintain joint self-attention, meaning the visual center and the text center are still constantly talking to each other and sharing context, even though they process their specific data independently. Now, why does this architectural choice matter so much? Mostly because it stops capacity competition. If you force an AI to learn advanced grammar and how to paint a realistic dog using the exact same parameters, those skills fight for space in the network. One degrades the other. ModT prevents this, which significantly improves generation quality across the board. Even better, it allows for asynchronous training. This is so cool. You can actually take a perfectly trained, highly intelligent text model, freeze its brain, and just bolt on a newly trained image generation module without destroying its ability to write and reason.
And the versatility of this approach is just staggering. This exact same separated parameter logic isn't just for making pretty pictures or chatting. In embodied AI, we're talking robotics here. Engineers are using this architecture to predict a totally different modality. Instead of generating image patches, the model generates physical robotic action vectors. It uses its text reasoning center to figure out what the goal is, and a specialized modality path to tell a physical robotic arm exactly how to move in 3D space to achieve it.
Section 5. The next AI frontier. The unsolved mysteries of multimodal reasoning. So, we have come incredibly far. But what is still missing in our quest for true physical intelligence? Well, while digital processing is advancing rapidly, real-world physical logic is still very much an open problem. We still haven't mastered spatial temporal understanding, like truly knowing how physical objects relate to each other in 3D space over time. Second, as we touched on earlier, if you train a model really hard on image generation, it doesn't positively transfer over to make the model smarter at image understanding. They're disconnected. And perhaps the most fascinating mystery of all, next frame video prediction doesn't naturally create reasoning skills. Think about this. If you make an AI predict the next word in a sentence for billions of pages, it gets incredibly smart and learns logic. But if you make an AI predict the next frame in a video for millions of hours, it just gets really good at generating video. It doesn't magically learn underlying physical reasoning. And that dilemma points to a really fascinating theory. Berkeley professor Sergey Levine frames it beautifully. He suggests that language is fundamentally different from sensory data. Language is a highly compressed abstraction of human cognition. When an AI learns text, it is basically reverse engineering the human reasoning process itself. We baked our logic into our words. Images and videos, however, they're just passive sensory observations of the world. They completely lack the inherent structured logic that human language contains. Which leaves us with this final, profound question to ponder today. Can an AI truly learn to reason just by passively watching the world? Or will human language always be the necessary skeleton for true intelligence? As researchers race to build native multimodal models that can finally interact seamlessly with our chaotic physical reality, the answer to that question might literally define the future of artificial intelligence. Thank you so much for joining me for this explainer. Keep asking questions, and I will catch you on the next one.